So hi everyone, my name is Sourour Elloumi. I'm from Insta Paris. My talk is on quadratic convex reformulation for quadratic and polynomial problems with binary variables. So the outline is as follows. First, I will introduce rapidly the problem. And in part 2, I will present quadratic convex reformulation for binary quadratic programming. And in part 3, the extension to polynomials. So here I just recall briefly the taxonomy of quadratic programming. So we have the case where the constraints, you have linear constraints, a quadratic objective function and continuous variable. So this is named convex QP in general. If the quadratic form is convex and non-convex QP otherwise. When you have some quadratic constraints, if convex is quadratically constrained programs and non-convex otherwise. And when we have integer variables, if your forms are convex, you are in the case of mixed integer quadratic programs or quadratically constrained programs, and otherwise you are in the non-convex case. So the interesting thing is that here I draw a wall between the case where your quadratic forms are convex or not. Because here the green case is the easy case, the red case is the hard case, and this case is between the two, because you can rely for these problems. In fact, you have non-convexities. These are not convex problems, but they are non-convex since you have integer variables. The difference with those ones is that you have you can rely on continuous relaxation in order to solve your problem by branch and bound, because when you relax the integrality constraints, you have quadratic problems. So this makes the difference between those problems and those ones. What happens for when you have only binary variables is that you obtain a very particular case where you can both linearize or convexify your problem. So the word linearize here means reformulate equivalently into a MINLP. And convexify means reformulate equivalently into a convex MIQP. So here I take the easy case where we have only a quadratic form and binary variables. And what you can do when linearizing is just replace every product of two variables by a new one and add those linear inequalities. So this is very common. And it is very well known that for any feasible solution, you have from these equalities, you can deduce this, you have this relation between the new variables and the product of variables. So this is this problem is equivalent to the first one, because by solving this problem, you solve the initial one. So this is linearization. Convexification consists in transforming the quadratic form in order to make it convex. And here it is very easy because you can add those terms to your function. those terms are equal to 0, in fact, in any feasible solution, just because your variables are binary, and so squaring the variable is equal to the variable itself. So you have here quadratic forms that which value is 0, and what you do here is that you push you can push the diagonal terms of your Hessian matrix. So this is the quadratic part of the reformulated function, in such a way that your matrix, your new Hessian function is positive semi-definite, so the function is convex, and this can be done just by putting lambda equal to the smallest eigenvalue of your initial matrix Q. So this reformulation is very easy. This quadratic reformulation is very easy, and it uses only the initial variables of the problem, so the x variables. Here this is an illustration of this, because when you have an initial non-convex function, doing this convexification gives you a convex function, but satisfying the fact that when your x variable, when your variable is 0 or 1, so for those feasible solutions, the two functions have the same value. So the two functions are perfectly equivalent for binary variables. So a general question may be, given a quadratic problem with binary variables, is it better to linearize or convexify? Actually, there is no easy relationship between the two methods. Sometimes the first one, linearization, is better than convexification, and sometimes it's the reverse. And what we do what we call quadratic convex reformulation method, QCR, is to get a method which is provably better than both of them, at least in the sense of the lower bounds they lead to, the lower bounds they use. So quadratic convex relaxation uses the same idea as the smallest eigenvalue method, but it the trick is only to choose non-uniform scalars to change the diagonal terms of the Hessian matrix. So rather than having a scalar lambda here, you have different values on your diagonal terms. And again, for the same reason as before, the function, this parameterized function by u is equivalent to the first one, because this is equal to 0. And your concern now is to get such vectors u, making the function convex, and this is your first concern. The second one is to make the continuous relaxation bound as tight as possible. In fact, you want a vector u such that the function is convex, but also such that the bound that you get by solving the convex relaxation, the quadratic convex relaxation. So when you relax the integrality constraints, you want to have a bound that is as large as possible. And solving problem P was proved in method QCR. This is the essence of method QCR, quadratic convex reformation. So it's to prove that the theorem, this theorem saying that problem P, so this problem of finding the best vector U, you can find it from the solution of an SDP relaxation of problem P. This SDP relaxation is the easiest one. It consists only to relax the equality large X equal to XX transpose and to fix the diagonal terms of this matrix X to the small X variables. So when you solve this semi-definite programming relaxation, or precisely its dual problem, you can deduce your vector U of parameters from the dual solution of the SDP problem. So you have a two-phase method where in the first step you solve the SDP, you deduce the best vector U, and from this vector U star you build the new equivalent problem, which is quadratic and convex. And now you can solve the MIQP. So it's an MIQP that can be solved by branch and bound, and each bound of the branch and bound, you solve a quadratic convex problem. And the interesting thing is that at the root node of this branch and bound, the bound is equal to the SDP bound. So the bound at the root is tight. How to improve? Our improved version of QCR takes into account actually mixed integer variables. So we call it mixed integer QCR, but it can be seen as just an improvement of the first method, and the improvement from the fact that we can also build other quadratic function from linear equalities. So this is the first improvement. And the second one comes from the fact that now we want to make every possible change in the Hessian matrix. So we tolerate any improvement, any change in any entry of that matrix. And for this, we consider new variables, y, that will be equal to the product of variables in order to be able to build an equivalent function. More precisely, we take, we do this transformation. In fact, we are given a matrix S, and we build this function, supposing that, or adding the condition that y ig is equal to the product of two variables I and j. And in fact, here you can, if you replace y by the products of the two variables, you can see that you can get rid of those terms and just have again your initial term qij multiplied by the product of the two variables. So it is easy to check that under these conditions, this function is precisely equivalent to the initial one. Okay, now the quadratic part of the function of this function is only this part. So it is convex if and only if matrix S is positive semi-definite. Now the problem, if S is convex, is PSD, the function is convex, but this is not convex. This equality is not convex, and as the variables are binary, we can replace by these inequalities, and we are done, because here we have a convex MIQP. So now the new question is how to choose matrix S in such a way that the continuous relaxation bound is as tight as possible. So we have here the same problem, and the theorem can be extended to that case. So to have the best matrix S, you have to solve this semi-definite programming problem. So which is an improved because it is more constrained version of the previous SDP program. So you have a tighter bound, and but the method works with the same steps. So first you solve this problem, or in other words, you solve a semi-definite programming problem, and in phase 2 you perform branch and bound, and you have the same equality at the root. So what we have to keep from this part is that this improved version of QCR is better than the first one, which is again better than the smallest eigenvalue. So all this by construction. But the new thing is that MIQCR is better than linearization. As I said before, linearization and QCR are not cannot be compared from the bound point of view, neither with the smallest eigenvalue. So to give you a precise, some numerical, a numerical example of the kind of bounds that you can get at the root of the branch and bound, this is an example with 70 variables and about 500 non-zeros, just a quadratic function with binary variables. And you can see here that linearization provides, you have, with linearization, you have 42% as error at the of gap, sorry, at the root node. With the smallest eigenvalue, you have 40% gap. With QCR, you have about 7% gap, and the gap from the improved version of QCR is less than 1%. So now, how to extend to polynomials with binary variables? I will show things on an example. So the main idea is that any polynomial with binary variables can be transformed into a quadratic function with some other constraints. So here on the example, you have a degree 3 monomial and a degree 4 monomial. You can replace the product x3, x4 by x5, both in this monomial and in this one. So you can you get here a monomial of degree 2, and here a monomial of degree 3. So again, you have x1, x2 that you replace by x6, x6, and now you have a quadratic function. So this you get a new, you get a quadratic function, but you added this quadratic relationship between your initial and your new variables. But this can again be linearized. So you add these constraints, these classical constraints, and you get a non-convex mixed integer quadratic problem, which is equivalent to the initial polynomial problem. The price of doing this is, of course, the fact that you add variables and constraints. You add there are several quadratization methods, but doing some easy things that the same easy thing that I'm doing here requires to add d minus 2 new variables for any degree d monomial. But of course, you can reuse the same variables if you have the same products in the polynomial. So our first step is quadratization. Once we have quadratized, you have here a non-convex mixed integer quadratic problem with 0 and 1 variables. But on this problem, you can apply our previous methods, QCR or the improved version of QCR. So what happens when we applied QCR to this quadratized problem is that we observed that the root bound was quite weak. But when you apply the improved version, the problem is huge. The SDP problem is huge, so we had difficulties to solve this problem. To give you an example, with the 60 variable here and about 52,000 monomials, we have an SDP with this number of variables, but about 3 million constraints. So this is a very large problem. So our concern was to find an SDP relaxation, which is of this new MINLP problem. An SDP problem, which is smaller than this, the one that we get here, but with a better, an improved bound if compared to QCR. So what we do is to use some other relationship relations between the initial variables and the additional ones. For example, here we can observe that if you take this product x3, x4, which has been replaced by x5, if you multiply this term, so if you multiply x5 by x3, because x3 squared is equal to x3, you again obtain the variable x5. So from this, you can deduce that x3, x5 is equal to x5, and this gives you a new constraints in your SDP program. So you have this new relation, this new equality in your SDP. And you can build several other ones with the same idea. So with very simple ideas from quadratic convex relaxation applied to polynomials, we applied it on this problem of low autocorrelation binary sequences, where the problem is to find the sequence of n digits equal to -1 or +1, such that this quadratic function is minimized. And this is a quadratic function with -1, +1 that we can reformulate with binary variables, obtaining this monomial of degree 4, this polynomial of degree 4. And we obtained very good results on the benchmark instances of this problem. So here we have a problem with n equals 35, where we were able to prove the optimality of the previously best known solution here. So this is our bound after some computation time in the branch bound. So you can see that the bound is better than improves the previously known lower bounds, and in this larger instance, we have improved both the best known solution value and the best lower bound. So again, here, this is our new gap compared to the best, the previously best one, which is here. So as conclusions, I will say that quadratic convex reformation provides a powerful exact solution method for these quadratic problems. It has been extended to any quadratic program with quadratic constraints and mixed integer variables. And as I said here, it is efficiently extended to polynomial with binary variables. But a new question may be raised here. What are good quadratization? So here, in our implementation, I quadratize with a very simple heuristic. So one can think about how to bestly quadratize the polynomial. And I finish with some references. And thank you for your listening, and see you one time in a true conference. Bye bye.